We're going to learn in this video today how to fine-tune large language models locally on our system using Unsloth in Python. Now, Unsloth is a library that allows for accelerated fine-tuning. It massively speeds up training time. It also reduces VRAM usage, so the GPU memory that is being used, by 50 to 80% is what I read. It does that by using techniques like 4-bit QLoRa, gradient checkpointing, CPU offloading, and so on. But essentially, it allows us, if we have at least some decent hardware, to fine-tune models locally on our system. If you don't have the hardware, you can also use for free a Google Colab notebook, so you can also follow this tutorial if you don't have a decent GPU on your system or in your system. And what we're going to do is we're going to see how this is done, and then we're going to take the resulting model, export it, change the format, and then import it to Ollama so we can use it locally on our system. So let us get right into it. Alright, so we're going to learn how to use Unsloth to fine-tune large language models in Python today. As I already mentioned, Unsloth is a Python library that allows us to do accelerated fine-tuning. It saves a lot of VRAM, it speeds up the training process. And for those of you who don't know what the idea of fine-tuning is, it's we take a model that is already pre-trained, that already has some intelligence in it. For example, a Phi model, a Mistral model, a Quen model, preferably open source or usually open source because we have the model parameters. And then what we do is we further train that model, we tune these parameters, or in the case of LoRa and QLoRa, we don't tune the parameters directly, but via low-rank matrices. I have a video where I go into detail if you want to know how LoRa works behind the scenes. But essentially, we're training the model to perform better at a set of tasks that we submit to the model. So we use some examples where we do something, where we show the model how to do something that it is not capable of doing, or at least it doesn't do it as well as we would like it to do it. And we provide the model with additional training examples to fine-tune these parameters, to make some adjustments in the model parameters, and to perform better at the tasks that we train the model on. Now, sometimes this leads to the model being worse at everything else, so it decreases the performance of the model when it comes to more general tasks. So for example, if I train a model to extract information from a contract, maybe it can do that very well afterwards, but it doesn't know how to answer some very basic question about geography, for example, or it does that in a very odd format. So this is a trade-off that you need to keep in mind. Fine-tuning a model usually makes it better on or at a specific task, but it may decrease the performance overall if you want to apply this to other use cases, even though maybe the base model, the base pre-trained model was quite good at everything else as well. So this is just something to keep in mind, but I don't want to talk too much here about the theory. I would like to get right into it. And the first thing is we need to figure out, or you need to figure out, if you are going to do this locally on your system or if you're going to do this in a Google Colab notebook. Because for this process of fine-tuning, you will need to have a GPU that is capable of doing that. So you need a certain amount of VRAM, you need to have CUDA support, and if you don't have that on your system, you have to use something else. You can do that for free with a Google Colab notebook, but for example, if I have here now with NVIDIA SMI, you can see I have a 3060 Ti, and I have actually, OBS is using quite a bit of VRAM, so maybe I'm going to run into some issues while recording here. But essentially, you have your GPU displayed here. If you use NVIDIA SMI, at least on Linux and Mac, on Windows, there's probably some GUI software that you can use to figure out what GPU you have and what the VRAM usage is. But with this GPU, 8 GB of VRAM, GeForce RTX 3060 Ti, I can do this, and you can probably do this as well if you have some GPU that is similar to this one. Otherwise, as I said, if you don't have the resources necessary to do that, you can go to Google Colab. Here you can just open up a new notebook. You don't have to pay anything, you just need a Google account. And in the notebook, then you can go up here to connect, or actually to the arrow besides connect. You can say change runtime type, and you can switch to the T4 GPU. By doing that, this is going to start a new Python kernel, and you're going to be able to use the NVIDIA GPU in Google Colab. It's not going to be the fastest environment. You're going to have more waiting time, I guess, but you can do it for free and you don't need to have the hardware yourself. So once you have decided whether you're going to do this locally or in a Google Colab notebook, the next decision is the model that you want to use, the base model that you want to use for fine-tuning. In my case here, I'm going to use the Phi 3 Mini 4K Instruct BNB, so bits and bytes 4-bit. What this basically means, it's the Phi 3 Mini model. It has a 4K context window, I think, is what the 4K stands for. Instruct means it's instruct trained, so we have a model that is trained for user interaction, for query and response for prompt and response, and BNB 4-bit basically just means bits and bytes quantized 4-bit quantization. That is the model that I'm going to use. What you want to do for sure is you want to use an Unsloth model. So you want to go to Unsloth and you want to use a model from their collections here. You don't want to use a model that is not from Unsloth. So it has to be compatible here. Make sure you use an Unsloth model. And this one is a decent model that we can use. And the next thing, once you have decided on the model and on the development environment, is the dataset that you want to use. Now, this here is totally up to you. You can use any dataset you like. I personally am going to use a very simple use case. I already have this in my tutorial directory. So in here, I have a JSON file, peopledata.json, and the structure is very simple. We have a list, and then we have individual dictionaries in here that have a prompt field and a response field. So this is what we provide to the model. And this is what we get as a response from the model. This is how we teach the model what kind of response we're interested in. I want to provide a message like, while strolling through a botanical garden, Igor, now 20, earns a living as a tour guide. He is known amongst friends for conducting amateur astronomy observations in quiet solitude. Okay, so very long text with a lot of content, but the important thing to me is I want to have a name, an age, a job, and a gender. That is what I'm trying to extract here from this message. And I have a bunch of examples that I generated with a large language model, so nothing that I typed myself. The basic idea here is I want to train the model to just get information about a person, and as a result, even without instructions, even without telling the model, hey, extract information, just always return a JSON object with these fields. So this is not a very useful example. Probably the model can also do that by just giving it some additional context in the prompt. But I want to show you just the principle, and then you can apply that to anything else. So you can either do that in the same way by trying to fine-tune a specific format into the model, or you can also just try to use this on legal documents. Maybe the model doesn't understand legal documents. You have a bunch of legal documents. You want to extract information. And what you do is you provide the document text and then the answer that you're looking for. By doing that, you teach it about concepts, or it's fine-tuned on specific concepts that occur in legal documents. That would be another use case. But this one is simple and easy to see if it works, because by default, if I provide something like this, the answer is probably going to be I don't know, a question or a summary or something. It's not going to be a JSON object with these 4 fields. And after fine-tuning, that should be the case. So this is the dataset I'm going to use. You will find also a link to the GitHub repository in the description down below if you want to use the exact same dataset. Otherwise, feel free to just generate your own. In my case here, I have the key prompt and response, or the 2 keys, prompt and response, for the user message and for the output of the large language model. Once you have that, the only thing left to do is to set up your environment. So again, if you're using a Google Colab notebook, just go into the notebook, change the runtime, and then install packages if necessary. Just !pip install, and then Unsloth. And I think this should install all the other dependencies if I'm not mistaken. Locally, of course, you do the same thing in the command line. So pip or pip3 install Unsloth. I think, again, this should install all the dependencies that are necessary for this tutorial today. If you want to use a virtual environment, you know how to do it. Python or python 3-m-venv.venv. And as always, I'm going to use UV. You don't have to use UV, but in my case, I'm going to initialize a UV project. And instead of saying pip3 install, I'm going to say UV add Unsloth, which has the same effect. It's just in this isolated environment. Then I'm going to say activate my virtual environment. And now one more thing that I'm going to need here, and that you're also going to need if you want to use the same development environment, is since we're going to work in interactive Python notebooks, I like to work with the Jupyter Lab environment. So I'm going to say UV add, and in your case, pip or pip3 install Jupyter Lab, like this. And then I can just say Jupyter Lab, and this is going to open up in the browser now the Jupyter Lab environment. Let me just take the command line and put it to a different workspace. And here now I'm just going to create a Python notebook. So an IPython notebook, interactive Python notebook. I'm going to call this main. And here now we're going to write our code in the same directory. Remember, I have my dataset, people data, JSON, with all these prompts and responses. So that is going to be what I use here for training. And the rest is going to be just code in this notebook. So the first thing that we want to do is we want to load our JSON data and get it into a format that we can use for fine tuning. So we want to turn it into a data set that is compatible with the Hugging Face ecosystem. And we can do that by, first of all, importing JSON from core Python and also importing from datasets, which is a Hugging Face package, the dataset class. And this, of course, is installed automatically when we install Unsloth. So once we have that, we're going to say with open people data.json in reading mode as f. We're going to say the data is equal to JSON, load the content of the file stream f. And now what I want to do is I want to take the individual examples and turn them into formatted strings, which I can then turn into a data set that can be used for fine tuning. So we're going to say tuning examples is equal to an empty list. And then we're going to iteratively fill up the list with formatted strings. So I'm going to say for example in data, tuning examples, append, and then the formatted string is going to be starting with a tag. So angle brackets, double pipes, user, \n, curly brackets, example, and then here the prompt. So the idea is I know the user is sending this prompt. Okay, after that, another \n, angle brackets, double pipes in between assistant. So the response of the assistant, \n is, and then curly brackets again. Now, since the response is a JSON object, we have to use the dump s function. So dump as a string. So JSON dump s example response. And finally, also angle brackets, double pipes, end of text. So that is just the interaction formatted as a string. So again, we just have a user flag, new line, example prompt. So the field that we have in our data set here, this text here. Then we have assistant or line break assistant. Then we have this information here as a string, so as a JSON string. And then we have just end of text without a line break in between. That is how we structure our data here as a string or as multiple strings. And once we have this list filled up, we're going to say dataset is equal to dataset from dictionary. And we're going to pass here a dictionary with a field text, which points to tuning examples. Just a quick note from future me here, even though the approach that we use in this tutorial works perfectly fine for this use case, it was a little bit rushed and there's a more professional way to do it. What you want to do is you want to first load the model and the tokenizer, and then when preparing the dataset, instead of specifying your own custom tags, you want to use the chat template that is provided by the tokenizer. Here you can see how this is done. We just have a basic helper function. It takes the response, it takes the prompt, and we structure this in a message list, so with role user, role assistant, and the content in the same way that we do that when using various APIs. And then what we do is we say text points to tokenizer.apply chat template, and then we provide the messages in here. This is more professional and works for all sorts of models without introducing any problematic tokens. So even though it works perfectly fine how we did it in this tutorial, that would be the more professional way to do it. And I would encourage you to try to do the same project with this code. You can just replace the code like this and you will still be able to work with the data set later on. Then we need to specify what language model we want to use. So we're going to say from Unsloth import fast language model. Why do I not get auto completion? Okay, doesn't matter. Fast language model. And we're going to get as a result of this model and tokenizer. So the tokenizer takes text and encodes it as tokens. And the model itself is the model itself, obviously. So fast language model from underscore pre-trained. Now, the first argument here, the first keyword argument is the most important one, which is the model that we want to use. In our case, we're going to use the Unsloth Phi3 Mini 4K Instruct BNB 4-bit. So I'm going to copy that here. I'm going to paste this as a string. So you just need the identifier here for Hugging Face to pull the model. Then we can specify the maximum sequence length. So I'm going to say max underscore sequence underscore length is equal to 248. I'm going to say the data type is equal to none, which means it's going to use the default or it's going to automatically decide on that. And I'm going to say load in for bit is equal to true. So that is going to load the 4-bit quantized model. Okay, actually I messed up the keyword argument. It's not model, it's model name. And also it's not load in 4_bit, it's load in 4-bit. And there you go. So once we have this model downloaded and loaded from the pre-trained Hugging Face model, we're going to turn it into a parameter efficient fine-tuning model. So we're going to prepare it for fine-tuning using LoRa, or QLoRa to be precise. We're going to do that by saying model is equal to fast language model get_PEFT, so parameter efficient fine-tuning model. And here now we have to specify the LoRa parameters. The most important one being the rank of the matrices. Again, if you're interested in the idea behind LoRa in more detail, I have a video on that. But essentially, LoRa works with low rank matrices, so with small matrices where we train just a small set of parameters. And depending on the rank size we choose, this is basically a trade-off between speed and complexity. The larger the rank size, the more complex the knowledge that can be learned, and the smaller the rank size, the faster the fine-tuning. So here now we're going to go with 64. Then we're going to say target_modules. This is basically choosing the modules where we're going to inject LoRa matrices. We're just going to type out the stuff here. So if you want to understand this, again, I have a LoRa tutorial where I explain this in a little bit more detail. But basically, we're going to go with the query projection. We're going to go with the key projection. We're going to go with the value projection, and also a couple of layers where I don't really know what they stand for. O projection, gate projection, up projection. I think it stands for projection, and then down projection. Also, of course, don't forget to add the model itself. So this has to be applied to the model. So the first parameter here, positional, is the model. The second one, already a keyword argument, the rank, then the target modules. Then we're going to provide the scaling factor, LoRa_alpha, which is usually just the rank size times 2. So 64 times 2. Then we're going to say LoRa dropout equals 0. So we're going to have no regularization. It's going to be deterministic on this front. We can, of course, tweak this parameter to have more regularization if we want to. Then we're going to say here bias is equal to none. We're only going to apply this to the weights. And then we're going to say use gradient checkpointing is going to be equal to Unsloth. So we're going to use this efficient Unsloth gradient checkpointing that reduces VRAM usage. So these are reasonable parameters. Of course, you can play around with that if you want to. And once we have that, we can move on to the trainers. So once this model is prepared for fine-tuning, we can create a trainer with a config. And for that, we're going to say here from TRL import SFT trainer. So supervised fine-tuning trainer, and SFT config, supervised fine-tuning config. And then we can go ahead and say trainer is equal to SFT trainer. In here now, we're going to provide, of course, the model. So model is equal to model. Then the train data set that we want to do the fine-tuning based on is the data set. This is why we have to prepare it, because here we can just pass a Hugging Face data set. Then we want to say tokenizer is equal to tokenizer. This is what we get also here from the pre-trained model. Then we're going to specify the field that contains the text. So that is going to be the dataset text field. In our case, we call this text. This is what we specified here when we set from dictionary. And of course, also we want to specify the max sequence length, which is still 2048. Now we specify some arguments here, which is the SFT config. And the SFT config is a constructor here where we pass keyword arguments again. So the first one is the per device train batch size. So how many sequences do we want to read at once in the GPU? We're going to go with 2. And then we also have the gradient accumulation steps. This is essentially how many iterations we're going to accumulate before we take a step with the optimizer. We're going to go with 4. Basically, this leaves the effective batch size to be 8, so 2 times 4. Then we define a parameter called warm-up steps. This basically means we start with a learning rate of 0 and linearly climb up to the learning rate that is specified. We're going to go here with the default. We're not going to manually specify a learning rate, but essentially for the first 10 steps, what this means is we're going to increase the learning rate until we get to the desired learning rate. And then we're also going to specify maximum steps. We do also specify later on here the epochs, but basically when you specify the number of epochs and the max steps, you just terminate when one of the two is reached. So I'm going to go with 60 steps maximum. I'm also going to go with number of train epochs 3. So probably the 60 steps are going to be before the 3 epochs are over. Then I'm going to also say logging steps is 1, so we want to log every single step. And then I'm going to specify the output directory, so where we put all the logs and all the checkpoints and so on. That's going to be outputs. The optimizer itself, so the optim is going to be atom with weight decay. I think this is what atom W was, so atom W 8-bit quantization. And that is basically it. So we can create this trainer, and once we have it, we can say trainer.train, and this is going to do the fine-tuning for us. So you can see it starts logging the steps. We can also see how the loss goes down, and this will take 60 steps. And once it's done, we're going to be able to work with the model. So now we're done with the training. When we scroll down here, we can see we end up with a loss of 0.667. Now, is that good or not? We can test that out because this fine-tuned model can now be used directly in Python, or it can be exported and used in Ollama. We're going to do both things, but first of all, I want to show you how to use that in Python. The first thing we need to do is we need to set it to inference mode by saying fast language model for inference model. And then we can craft an example message or an example conversation. So we're going to say messages is equal to a list. In this list, we have the message role, or the message which is a dictionary. Role is going to be the user providing a message, and the content is going to be some message about a person. For example, Mike is a 30-year-old programmer. He loves hiking, so this is irrelevant information. And then actually we have everything now. We have the age, the job, and some irrelevant information. The gender should also be derived from he, and Mike is the name. So let's do that. And with these messages now, or with this message example now, what we can do is we can take it, we can apply a chat template, we can feed it into the model, we can get the response, decode it, and see what the model answers. So we're going to say inputs is equal to tokenizer dot apply chat template to the messages. Tokenize is equal to true. Add generation prompt is equal to true. Return tensors in PyTorch format, so PT, and put the whole thing onto the GPU, so 2, and as a string here, CUDA, to get this to the GPU. These are now the inputs. We take these inputs, we feed them into the model, and we get the outputs. So we're going to say output is equal, or outputs is equal to model.generate input underscore IDs is equal to inputs. Actually, let's not use white spaces here. And then we're going to say max new tokens. So don't generate more than, let's say, 512 tokens. Use caching. So use cache equals true. Then temperature. So how creative the model can be. Temperature. A good default value is 0.7, I guess. Then we're going to go with sample, or actually it was do sample equals true. So it's going to be some randomness in here. And we're going to say that we want to sample in a way that we get the smallest set where the cumulative probability is at least 0.9. So I'm going to say top underscore p is equal to 0.9. So maybe let me zoom out a little bit so you can see the whole line. Outputs is model, generate input IDs, inputs, max new tokens 512, use cache true, temperature 0.7, do sample true, and top p is 0.9. And once we have that, we have to decode that. So we're going to say here response, let me zoom in again. Response is equal to tokenizer dot batch decode. And we're going to decode the outputs, and we're going to get the first instance of this list or set. And then we're going to print response. So the result of that will be, this is what the user says, and the assistant then says, name, Mike, age 30, job, programmer, gender, male. Perfect. So this is the fine-tuned model doing what it's supposed to do. Now we can export that and import that into Ollama. And the code for that is super simple, but maybe you have a problem with your GPU VRAM. So you might want to add, or you might have to add a parameter, a keyword argument to not run into problems with your GPU. So what I'm going to say here now is I'm going to say model.save pre-trained gguf, which is the Llama CCP format. And here we're going to say now what we want to call this. Let's call this fine-tuned model, like this. We're going to also pass the tokenizer, and we're going to pass a quantization method. So quantization underscore method, and this is a string. Now these strings have some logic to them. If you say Q4, that's basically a 4-bit quantization. Then the key, the K, I forgot what it exactly stands for. It was something with a key value approach. I'm not entirely sure what it was exactly. And M is medium size, so that's a decent quantization. And now to not overload your GPU, what you can do, you can try it like this. If it works, fine. If you run out of memory, what you want to do is you want to say maximum memory usage, and then you want to provide a percentage how much of your memory should be used. In my case, I'm going to go with something low like 0.3. The rest of that will be used by the CPU or done with the CPU. So let's see actually while I'm recording how much I have left here. Not a lot, so probably it's going to even crash with that. So I can give it a try. If it doesn't work, I will have to stop the recording, do it, and then start recording again. But let's see. So what it does here is it downloads Llama CPP if it's not installed on your system. So it's going to do that, but you can see already out of memory. So what I'm going to do is I'm going to stop recording. I'm going to close OBS. I'm going to run this again, and then I'm going to go back to recording. All right, so the model was exported successfully. We can scroll down here. This is what it looks like. It exports everything step by step, and in the end, it's done. The output location here is the fine-tuned model directory. And now what we can do with that is we can take that gguf model and turn it into something that can be loaded into Ollama, and then we can just easily use it in Ollama. So I'm going to close the browser. I'm going to open up my terminal. I'm going to navigate to my tutorial directory, and this is now super simple. Now I'm not going to install, or I'm not going to go through Ollama. Ollama is super easy to install. You just have to go to the website. You can click on macOS, Linux, or Windows, follow the instructions. You have Ollama on your system. In my case, I think I installed it from the AUR on Arch, by the way. Once you have this, you can just run Ollama. So Ollama serve. Now Ollama is running, or you have it as a service running all the time. And the only thing that you need to do in order to create now or to load the model into Ollama is you need to create a model file with a single line of code, so to say. So model file with a capital M, model file like this. And here we just say from and the path to our model. In our case, this is now fine. Actually, I forgot the exact path. So let me just check that out. It's fine-tuned model, and in here we have a file called unsloth.q4kmgguf. This is the one that we're interested in. So fine-tuned underscore model slash unsloth.q4 underscore k underscore m dot gguf. That is it. Now we can close that. And the only thing that we need to do now is we need to load this model file with Ollama. So we need to say Ollama create, and then we can give it a name, fine-tuned model -f model file. So what this does is it takes that, it creates an Ollama model. If I say Ollama list, I can now see that I have this model loaded here. And what I can do now is I can say Ollama run fine-tuned model. And now I can chat with this model in the command line. And if I say something like, Mike likes to go hiking when he is not in his day job as a software engineer. Next year, he celebrates his 30th birthday, meaning he's 29. Let's see if the model can understand this. So I can just send this, and as a response here, I get name, age, job, gender. I also get some more stuff, so it's not perfect. We can see, first of all, it didn't recognize that Mike is 29 because next year he celebrates his 30th birthday. And also it added some stuff that was not part of the training data. But you can definitely see that the fine-tuning had an effect, because if I just feed this into a raw model, it's going to give me some different response, like, hey, Mike is cool, or do you have some other information about Mike, or summarizes the text or something. This here is now structured output. Now we can actually clear the context and try again with the same message. This time I get 29. And I also get the correct model. So it's also a matter of randomness here, but I get now name, Mike, age 29, job, software engineer. It didn't recognize the gender, even though I said he. So yeah, maybe that's not perfect. The problem with this now is, I'm not sure if this is going to trigger the problem, but if I now say, who is Linus Torvalds, I'm not sure if it's going to be able to answer that. Okay, actually it does answer it correctly, but I also had the problem or the experience that when you ask it and it's fine-tuned, it will just give you name, Linus, age, maybe the age of Linus, but in this case it performs quite well. Let's try to say, who is Barack Obama? Okay, still manages to do that, so in this case it is not catastrophic. Besides that, let's try again something more comprehensive. Let's say John is going to celebrate his 50th birthday 2 years from now. He loves gaming and coding in his free time. He also occasionally teaches guitar for free, but his main job is clerk, for example. And we get here name, age 28, which doesn't make a lot of sense. Job clerk, and we don't have a gender. Yeah, it's not perfect. Maybe you need more data, maybe you need a better model, maybe you need different parameters, but the fact is fine-tuning worked. It's a science, it's an art to do fine-tuning properly, but you can see this is how you do it, and this is how you can also take the fine-tuned model and run it in Ollama locally on your system. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and bye.